Hi, everybody. Mr. Rubo here. And today, we're going to continue with quadrilaterals. And we're going to start on 5-24. So we've done coordinate proofs before. Okay. And so we're going to just kind of touch base on them again this time with quadrilaterals. So it says here, given quadrilateral ABCD with coordinates -2, 5, 2, 7, 4, 3, and -2, -5. We will hopefully plot these. Oops, having issues with my stylus there. Okay, and when you plot them, and actually, let me see. I'm going to show you guys the answer, so pretend you don't see them. So if you plot them and like you plot it nice, you see it looks like a kite. Okay, but we can't assume that. So we have to show that AB is the same as BC. We also have to show that AD is the same as CD. And when it comes to coordinate proofs, the easiest way of showing that is distance formula. So you could see here, I've done it for AB and BC. They ended up being the same. CD and AD, they also ended up being the same. So that is how I said it was a kite. Okay. We've done it before. We'll keep doing them. It's no different. You're most likely they're going to do distance formula, or if you have a question like B, what do you know about AC and BD? Well, if we look at AC and BD, those are the diagonals. And if you remember from yesterday, we know they are perpendicular bisectors because it's a kite. But we have to justify with the coordinate proof to show that they are perpendicular bisectors. We need to show two things. We need to show, one, we already have the sides. So like we know that AB is congruent to BC. We know that AD is congruent to CD. But we can easily find the slope, which they're perpendicular, -1/3 and 3. And then we can also see that it does bisect as well, because we can find the center where those two lines intersect is 1, 4, and do the distance formula from A to E, and then E to C, it ends up you get the same number, square root of 10. And this is the coordinate proof. You could also have proven it based on our information by HL once you have that, hey, they're right angles, right? And we actually get that the two triangles are congruent by HL is, I guess, more so what more important thing about that. All right, and then, and what did we just prove? We just proved equidistant, right? So that is exactly what equidistant was. I know when we might have mentioned it when we were doing it. The picture most of the time actually does look like a kite, okay? But we just proved it with coordinate proofs, okay? All right, so now we're going to jump back a few pages to page 11 and 12. Now, 11 and 12, there's no problems on here. This is more so for you just to kind of read and make sure you understand all of these things. So these are what we're going to do, and you'll kind of see what's underlined. It's for our proofs, what we need to show to prove each of the quadrilaterals. So for a parallelogram, we can show opposite sides are congruent. We could show opposite sides are parallel. We can show opposite angles are congruent. We can show if we have one pair of parallel sides and those same sides are congruent, then it is also a parallelogram. And then the last thing we can also show is if their diagonals bisect each other, then it's a parallelogram. So in a proof, you need to show any one of these five, just one of the five, and then you know it's a parallelogram. All right. If you're trying to prove something is a rectangle, you'll notice I circled the first two where it says parallelogram. They're also starred because you have to show it's a parallelogram first. And then if you show that it has one right angle, then you could say it's a rectangle. Same thing with number 2. You have to show it's a parallelogram and then show its diagonals are congruent. Then you know it's a rectangle. Or if it's possible, you might be able to show that all 4 angles are right angles. And that you could do even if you don't know it's a parallelogram. You actually can jump right to saying it's a rectangle if you know that. Okay. Then for kite, again, kite, you prove we have those pair of congruent consecutive sides. Okay. And yeah, a lot of times it's equidistant. Okay. Equidistant formula, right? And then the other way you prove it is actually if you have a perpendicular bisector. So if you used equidistant and say it's a perpendicular bisector, then you get that it's a kite. Okay. All right. Then to prove it's a rhombus, again, have the same qualification here. Parallelogram, parallelogram. So if it's a parallelogram, contains consecutive sides that are congruent. So you only have to show parallelogram and then that two sides next to each other are the same, then it's a rhombus. You don't have to show all four sides are the same. You just have to show two consecutive. All right. And then for number 2, if you show that the diagonals bisect the angles, it's also a rhombus after you've shown it's a parallelogram. And then if you're able to do number 3, which is if the diagonals of a quadrilateral are perpendicular bisectors of each other, then it is a rhombus. So they are perpendicularly bisecting both of them. Then you know it's a rhombus. And then finally a square for the nice shapes. Square is, you got to prove that it's a rectangle and a rhombus, and then you know it's a square. Okay. And then trapezoid, you just prove for isosceles. You have the legs are congruent, then it's isosceles. If the lower base angles are congruent, then it's isosceles. If the upper base angles are congruent, it's isosceles. And if the diagonals of a trapezoid are congruent, then it is isosceles as well. In each of these cases, you do have to show that it's a trapezoid. A lot of times they will give you that it's a trapezoid, but just prove that it's a trapezoid. You just have to show that one pair of sides is parallel. Okay, but most of the time they will just tell you. So let's go ahead and work through a proof here. So it tells us xy is congruent to kz, and z is the midpoint of kr. Triangle wxy, that top triangle, is isosceles with base xy, and then angle wxy is congruent to angle r. And we want to show that x, y, r, z, so this shape down here is a parallelogram. So again, always a good idea to plan through your proof. Well, having those congruent is nice, but we actually can get that kz and zr are congruent by the fact that we have a midpoint. So this is the same as that, which then by transitive, we get xy is congruent to zr. So that's important. And then we also have isosceles up here at the top, which means that these two angles, oops, that's not what I meant to do, that those angles are congruent, which then you actually get corresponding angles, right? So corresponding angles are congruent, meaning that these are parallel. So there's one way of proving it. There's other ways as well, but there was my plan. Let's see if that's the way we did it. Yep, so there's our, divides it into two congruent segments, transitive property. Yep, there's our triangles, isosceles. I actually went and said that I did the sides, but then I did switch to the angles, saying they're congruent. And then transitive property again. And yeah, corresponding angles are congruent. And then here's my reason. X, Y, R, Z is a parallelogram. If opposite sides are congruent and parallel, then they form a parallelogram. Okay. So again, I'll kind of scroll up just a little bit to give you a chance, if you need to, pause the video here to copy this down. And then again, pause the video here if you need to copy this down, but went through it up above with the steps there. Nothing really new up until, this we haven't used too much, and then this as well is brand new. So, but everything else we've used before. It's just now applying it to get a parallelogram. All right, and then our last page here, we are told it's a square. So we have square ABCD, so we actually know a ton of information. And then we are told E is the midpoint of AD, and then F is the midpoint of CD. We want to show that AF is congruent to BE. Okay, so we're trying to show that these are congruent. Okay, well, some of you might see, and we'll see if we work it out this way, that let's try to prove these two triangles are congruent, right? If we're able to prove those two overlapping triangles are congruent, that'll be super nice. Well, we know that all four sides are congruent because it's a square. So then like divisions, so we know those are congruent, right? And then we also know that, you know, this is the same as those two together, right? They're all the sides are congruent. So we can say AD is congruent to BA. We then can say AE is congruent to FD. So we have two sides, and well, I know all those angles are right angles. So that looks like side angle side to me. And then we have the two triangles are congruent, and then CPCTC. So let's see if that's the way we did it. Again, there might be a different way. We'll see. Square, perfect. If square, all sides are congruent. I listed just the sides I needed. So BA, I didn't list BC. BC, I don't, like, none of the triangles touch it, so I didn't need it. Okay. Then E is the midpoint, F is the midpoint, and I don't have to say that the two parts, so like AE and ED, are congruent. I don't have to say that because I have that their sides are congruent. So then I can just jump to the like divisions. I know some of you like to add those in. It's not wrong if you do. You're just adding a few extra steps. And then we have right angles because it's a square, right? If square, then all angles are right. And because we have right angles, those angles are indeed congruent. Now we do have to say that because we're using side angle side and not HL. And there's our side angle side, and then our CPCTC. So AF is congruent to BE. Okay. So thanks for watching and have a good day.